So welcome back. You'll give me a second chance. If you are interested, if I may, I'd like to. We were going slowly because, in part because I was being not clear enough. I want to finish up with why Diffinetti's model of imprecise probabilities, thought of as the range of provisions you have for a random variable that you have not tried precisely, is not something that gets us very far into the kind of imprecise probability theory that Seidenfeld is discussing. It looks like Diffinetti is taking it that way, but he doesn't, and he knows he doesn't. And in fact, later, as I say, in the 60s, he writes a paper with Savage saying the IP kind of stuff we saw we're discussing, don't do that. That's decision theory, in fact. So let me show you what it is that I think is on his mind, where he says this kind of range of probabilities interpretation is not to be understood. Why he wants not to go the way of real life. Just to remind you, we're gonna. I didn't define what maximizing expected utility, subjective expected utility thesis is when I said that you don't make book in the setting of Diffinetti when you're the customer. If you agree that the utilities are linear in the commodity, the payments are linear in the utility, you have no setting where you're obliged to make book. There may be some settings where you're allowed to make book, but then there are other options which don't make book and judge equally well. There's no setting where making book is uniquely best. And that's what we saw in the little example of 0.4 and 0.7. So again, the expected utility hypothesis is that the preference structure over acts are functions from states to outcomes, is such that there's a probability over the states. And what's key here is that there's no subscript on the P which reflects the act. That is, the probability on the states is a probability that's used in the representation of preference, which is not altered when you choose Act 1 or Act 2. Your probability on the states omega is the same whether you choose Act 1 or Act 2 or Act 3. So this kind of representation of subjective expected utility says there's a probability on the states and the utility, cardinal utility, von Neumann-Waldenstrom cardinal utility on the outcomes, such that the ranking of acts by this subjective probability expected utility, this subjective expected utility gives you back a qualitative ranking of preference. And what's key to note here is in this formulation of expected utility, the probability of the state doesn't depend on the act that's chosen, so we don't have any of that funny business of act-state dependence. And what we know is that when you don't have that, then strict dominance is a valid decision rule. So if you formulate partitions where you don't have act-state dependence, then you don't have to worry about the kind of problem we ran into at the beginning of the first session, where there's a further story that unsettles the legitimacy of the dominance principle. So that's a sufficient condition. I will say, I said most of these problems are like onions. So I've been emphasizing the need to watch out for act-state dependence when you're worried about dominance principles. We'll see that despite of all that, Diffinetti's notion of coherence is immune to concerns with act-state dependence. So let me say something. Having already said that dominance principles are sensitive to act-state dependence, I'm saying Diffinetti coherence, the kind of dominance Diffinetti is concerned about, is not subject to that concern. Let me show you what I mean. Suppose I'm asked to bet on whether author is going to raise his right hand next or raise his left hand next. And suppose it's got to be one in the next 30 seconds. And I give incoherent odds on that. And I don't know your name, or Piano is that's it. Is the customer. So I give him 0.7 on right and 0.4 on left. And he has an opportunity to make book against me, but author is in collusion with me. He will raise his right hand or left hand to make me do the best I can in Dennis. He will hear the bets that we make, and then he will raise it. The claim is, if I'm incoherent, there's nothing author can do to save my opinion. If I'm incoherent and you make hook against me, there's nothing author can do to save my life, save my betting. So that's a case in which my sure loss, we'll have to see, why is that the case? Why is sure loss in a Diffinetti setting? Why is uniform sure loss? And the way Diffinetti does it, it's not enough that it's uniform sure loss. There's something else going on, which allows the coherence to be immune to concerns with axis dependence. Very interesting twist. As I said, this is an onion, there are layers. We start by saying, oh, if you're going to use dominance, make sure you don't have axis dependence. Then Diffinetti introduces uniform dominance, very demanding. Uniform dominance by itself is not valid if there's axis dependence, but there's something else which does make it independent, insensitive to axis dependence. We'll come to that in a bit. Now, we aren't doing axiomatic versions of decision theory yet, such that what constraints are there on decisions that allow an expected utility representation. But basically, the expected utility theories that are axiomatized in terms of preference, if you start with preference and say, show me that there's a representation of this preference by expected utility, there are typically two axioms or very small variations on this which are core. One is a binariness condition, which is that preference is given by binary comparisons, weak order relation. This is one of the axioms that may be relaxed by IP theory when we do IP decision theory, because we can have pairs, triples of X, such that A and B are not compared, B and C are not compared by preference, by binary comparison. But you can't say they're indifferent because A and C are compared strictly. So A and C can be strictly better than A, even though we're using IP theory. But there's an event B which neither A and B are comparable, nor C and B are comparable. And so that non-comparability cannot be treated as a difference, if the difference is transitive. So axiom one is it's not the typical axiom that in IP theory, decision theorists go after, but it is one that you can go after. Of my teachers, Isaac Levi was very clear about wanting to relax axiom. Axiom two is a sort of cancellation of common parts, which is very common in measurement theory, going from qualitative to quantitative. You have some sort of concatenation operation, you put things together. You say, if I have A and B and C is some common third thing, C, then combining A with C and B with C should leave the relation between, should produce the same relation as A and B. The common part doesn't play a role. So A combined with C and B combined with C should have the same relation as A and B directly do to each other, because they only differ by this common part C. In the case of the kinds of decision theory we're looking at, this combination can sometimes be thought of as a mixed strategy or a mixture, where I take A with a certain probability and C with a certain probability, and then B with that same probability as A and C with the probability it had, and you say AC and BC have this common part C under this concatenation with the same probability I'm getting C. When I get C in both cases, who cares? And so I'm only worried about the part which compares A with B. That independence axiom, this is the one that typically is the subject of attack by those who want to move from expected utility to IP decision theory. And it's motivated typically by an Ellsberg style example. Ellsberg, I think, is the first one to have witnessed this. It was part of his PhD thesis in the early 60s. Same Daniel Ellsberg, by the way, is the Ellsberg of the Pentagon Papers. And he's alive and kicking. And if you're running a conference and you're doing anything related to sets of probabilities, you can invite him. We won't talk about sets of probabilities, we'll talk about political freedom and the things that are more important in his life. But he also does magic acts, so you can get a full evening of entertainment. We had him to the second SIPTA at Ithaca, Cornell, and he was invited to speak about what's become of decision theory in his contribution to sleep, and he spoke about political freedom, as I recall, and did magic acts on the side. Okay, so here's the Ellsberg problem. For those who know, its precursor is ALA. It's a bit simpler. And more to the point than LA, because there was only 2 prizes, where LA uses 3. And so it doesn't depend on cardinal utility. It's after the belief side of the story. So here's the situation. Formally, what's going on is we're going to have some events that have a precise probability and some events that don't. That's the transition from diffiniting. And we'll see that the way Ellsberg says people are allowed to choose a non-consistent with the diffiniting extension. So the idea is we have an urn. If you've not seen this, let me try and sketch it slow enough so that it makes sense. If you've seen it, then don't worry. So we've got an urn which has 90 balls, each of which are colored uniformly, one of 3 colors. So an urn is either red, white, or red, green, or blue. 1/3 of the balls in the urn are exactly 1/3 are red, and a ball will be drawn from the urn. So we have precise provision, the supposition of random, drawn at random, and see probability for each of the balls. So the probability or the price of red is determinate at 1/3. And then we've got the other 2 colors, green or blue, of the remaining 60. There's no information specified, and you might say, I know that a complementary event, green or blue, collectively has probability of 2/3, because red has probability 1/3 and it's red or. But the green, it can go from 0 to 2/3, and blue can go to 0 to 2/3 in the different sense of lower price. Look now at the following decision problem pair. You're asked to compare Acts 1 and Acts 2, and Acts 3 and Acts 4, and say, do you have preferences between them? Act 1 and Act 2. You're not to think of it as one of Act 1 and Act 2 and one of Act 3 and Act 4 together. It's just 2 separate decision problems. I'm asking you, how do you prefer between Act 1 and Act 2? How do you prefer between Act 3 and 4? Act 1 is a gamble with a precise expected value, because it's 1/3 1,000 and 2/3 0. So the price, I mean, it's the indicator for red is determined at 1/3, so it's expected utility, if we're using linear in money, is 1/3 of 1,000. Act 2, on the other hand, pays off the 1,000 looking at the indicator function for green and 0 otherwise. But green doesn't have a well-defined indicator function value, right? This could be anything between 0 and 2/3. So you're asked to choose between these 2. Act 3 and Act 4 are a bit more complicated. Act 4 is easy to describe. It says get the 1,000 if either green or blue and 0 if red. So that's using an event, an indicator that has a well-defined price of 2/3, because green or blue is the complement of red. We know that has a well-defined price of 2/3. On the other hand, Act 3, its lower expected value is 1/3, because we know there may be no blue, but there's at least 1/3 red. And it could go up to 1, so its range is 1/3. If we did a different extension at that point, its range is from 1/3 to 1. But it's 1/3, because even if there are no blue chips, the lower expected value is at least 1/3, because you have red underneath. And so you can approximate with red from below. And then you can only above, you can only approximate the short red, because blue could be all of the red chips. So it could go up to. Okay, so you're asked to choose between them, and it's quite clear what you're being asked to push. You're asked an attention between this range of expected utilities and something that is constant. And the sense is that if you're uncertain, and now we're using uncertainty to mean uncertain about the range of, about the expected utility, it's a different kind of uncertainty. Because there's no defined, you're not committed to a precise one, it's a different range. If you're asked to trade off feelings about or values of uncertainty about values of no uncertainty, in the sense that Acts 1 and Acts 4 have no uncertainty in the sense of range of expected utility. Their expected utility is robust under however you think the values. Okay, so the modal choice, you can put yourself through this if the numbers are done right, is that there's a modal choice for Act 1 over Act 2, the certainty associated with the risk, that is the fact that I have no concern about the proportion of blue or green in valuing Act 1, where I do in Act 2. That's worth something to me, at least in my preference structure, and I will give up the potential to win
have a 2/3 expectation of 1,000, which is possible under the specification of the problem if all the remaining chips are green, 2/3 of them are green. So I'll choose Act 1 over Act 2 and Act 4 over Act 3, where Act 4 over Act 3 is again this concern for precise expected, well-defined expected value. And here's just a graph of the expected utilities as X. X is the possible provision for green, which goes between 0 and 2/3. So Act 1 and Act 2, obviously if the probability assigned to green is less than 1/3, then I strictly prefer Act 1 over Act 2 by expected utility considerations. If that provision assigned to Act 2 is greater than 1/3, then betting on green is better than betting on red. And that's where it crosses over. At 1/3, I'm indifferent. It's 1/3 red, 1/3 green. Acts 3 and 4, you see cleverly constructed with the relation of the indeterminate one reversed. So for low probabilities of green, Act 3 is better than Act 4. Act 4 is the one which is for 2/3 because you're getting a chip if blue or green. And then Act 3's value drops down if the probability of green goes up. And what's interesting to see here is that if you fix X, which is what Diffinetti would say you should do, fix the value of X, think about it, come up with a provision for green. Whatever provision you pick for green, there's no value of X which puts 1 over 2 and 4 over 3. At best you can do is tie. If 1 and 2 are tied, then 3 and 4 are tied. I don't know if you've seen this before. If you have, this is just old news. But if you haven't, then you're seeing here that there's a tension between wanting to give a priority for the robust acts, robust in the sense that your uncertainty about green doesn't affect their value, which would be Act 1 and Act 4. You want to give a priority for those over the competing acts 2 and 3, where the dispreference is reflecting your dislike for the lack of robustness and uncertainty that it might be greater expected utility, it might be less until the value of X is specified. And I cannot recover that kind of overall preference in terms of a Diffinetti extension. So this is a typical example of why Diffinetti says, speaking for Diffinetti, I don't mean imprecise probabilities in the way those guys do. Referring to this community. We hope that this community, because you cannot extend and do the extension and make sense of the Ellsberg choice for 1 over 2 and 4. If you extend and make 1 better than 2, then you've made 3 better than 4. And if you've extended to make 4 better than 3, then you've made 2 better than 1. Any questions about the example? Now, the example is typically used to challenge the cancellation of common parts. And that's because you can, I haven't given you the slide, but it's easy enough to come up with. You can make acts 4 and 3, acts 1 and 2 mixed with some common part. Let's go back to the original payment structure and maybe you see it that way. Well, I didn't write out the chart. But if you write out the chart in terms of red, green, blue, and write the pairs of acts, you see the acts on the first 2 states are 1 is like 3 and 2 is like 4. It's just a question of what's going on in the 3rd state. And the 2 acts agree with each other, 1 and 2 and 3 and 4 agree with each other on what's happening in the 3rd state, but they give a different value for what they agree on. And that would be in violation. To think of 1 and 2 is different than 3 and 4 in preference, that is 1 to 2 differently than 3 to 4 would be violation of the cancellation of common parts. We can make up a table that shows that. So in terms of principle, yes.
Okay, so you showed quite convincingly that definitely would object against interpreting this fundamental theory as something for motivation for it.
Understood has been concerned about
Yeah.
robustness.
But would you say it's we should follow in this point, or leave definitely his opinion?
Well, if I honestly thought that we should not depart from Diffinetti, we could go to lunch and spend the whole afternoon doing the right thing. Because most of what I want to say is following the line that says Diffinetti's interpretation of his own integral theory is a possible one, but not required. And because it's not required, we have opportunities to do other kinds of things. So obviously, I'm not trying to say Diffinetti is right about this. I'm simply saying that it looks like Diffinetti is open the door to imprecise probability. But he quickly closes it by saying that's not what I mean by these. But mathematically, it's setting up exactly the kind of machinery that Berg was reviewing yesterday. It's just following that machinery in the direction of Diffinetti's. I don't want to know that.
Quite attractive, for instance, in machine learning, where we have very complex sample spaces. Just speak about what you know, and leave the rest for calculation. Very efficient way of constructing probability.
Yeah, but the question is, what are you allowed to say when the acts that you're comparing involve a part that are complex and have nuisance parameters? And when the nuisance parameters, they're nuisance parameters because in certain values this is better than that, in certain values that's better than this. And the question is, what do you do when you don't have a precise probability to average out the values of the nuisance parameters? Ellsberg type decision making say, I give priority to acts, I give priority to some acts because they avoid depending upon the nuisance parameter. That is, if the nuisance parameter here is the proportion of balls in the air that are green, that's a nuisance parameter in the sense that comparing Act 4 with Act 3 or Act 2 with Act 1, to make that comparison, I have to face the fact that X is a nuisance parameter. And if I don't know what X is, I get some contrasts that go one way, some that go the other. Diffinetti, Ellsberg is saying, in that case, it's legitimate to look at acts whose value is insensitive to that nuisance parameter. And Act 1 is insensitive to the proportion green, and Act 4 is insensitive to the proportion green. And it's appropriate, says Ellsberg, to allow preferences to reflect that robustness. And Diffinetti's theory says, no, sorry, no.
Sorry.
Yes.
He was trying to rescue axiom 2 by not allowing it precisely. But that's not part of his framework.
Well, no, because we can take all he's doing and say, we don't want to do that. We don't mean that the fundamental theorem should say you must pick a single precise value. That's what the fundamental theorem meant to Diffinetti. We're allowed to use that mathematics for a different purpose. A different purpose is not what Diffinetti was.
But does he have a representation theorem in his own framework?
Yes, given that you agree that the values associated with the rewards of linear utility, it's the representation theorem that's just coherent if your prices are expected utilities, you're making every gamble a fair gamble. And the reason that you have to make the gambles fair is because the gambles are unfair, then you're exposing yourself to both by being put on the disfavorable side of the gamble that you yourself are offering.
Just a question about how this notion of coherence relates to yesterday's notion. Naively, it seems that a set of prices is coherent if it gives rise to a set of gambles for the key that is desirable. That is coherent in the sense yesterday. But you said there are some differences.
Yes, there are some differences. The differences depend on what we're doing about infinite spaces, because Diffinetti requires uniform dominance. And that was not required yesterday. And so
Uniform notice over the.
that's right. So I mean, there are a number of the boundaries for, I mean, there are several differences. One is uniform dominance. That is, as I understand what was going on yesterday, if you looked at infinite spaces, and I compared the gamma constant 0 with the gamma 1 over n for infinite state space, or 1 over n and say omega n, then you would be required to say 1 over n is favorable, strictly favorable to 0. Infinity says no. And in fact, he has a theory, if you have the right kind of finitely additive probability, the 1 over n gamma gets assigned the value 0, just like 0. Its expected value is 0 for assigning probability 0 to the state, which is allowed under finite additivity. So I mean, there are differences like that crop up, but we're talking now about problems that one would expect to arise in the theory that has to deal with infinity. There's more than one way to deal with infinity. Infinity is concerned, what's driving infinity, he's filling out, he knows where the arrow has to land. The arrow has to land on allowing finitely additive probabilities. So he tinkers with the conditions so that they allow that arrow to land. And that means that he needs uniform dominance, not just simple.
Finite state spaces.
Finite state spaces, I think what's going, and there's one other, there's one other difference, and that has to do with the weak dominance. The discussion we had yesterday requires weak dominance. If you have a two-state space, E1, omega 1, omega 2, and the acts are the same on omega 1, but on omega 2, act 1 is better than act 2, then you have to prefer 1 to 2. Not for diffinity, because you're allowed to have probability 0 on that state 2. And then they would be judged indifferent.
I see, so here this framework, probability 0 actually means.
Probability 0 means it's possible.
But definitely also.
Yes, but not in that theory. Go ahead.
I think in theory that yesterday was used, you would separate out the difference beforehand and then go to that.
But the boundary on the first quadrant has to be labeled as strictly referred to 0 in your story and not in the definitive story. Because you could put probability 1 on the first state and 0 on the second state, in which case if the dominant, the vertical line over the origin would not be strictly referred to 0. That would be the indifference to it. Getting 0 in state 1 and something positive in state 2 or anything in state 2 is indifferent to getting 0 if all the probabilities on the state. And so I'm saying there are these mathematical questions about boundaries of sets and infinite state spaces. These, for our purposes, that's important. They have important mathematical consequences, but the idea otherwise, coherence is coherence. But there are differences. Okay, let's. So the one-sided prices that give us IP theory, not the way Diffinetti wants, but following a lot of what he's doing, is now I'm just repeating what you've seen yesterday. Take the merchant and allow the merchant to break up the fair price into two one-sided prices. Here's the maximum of my buying price. Here's the minimum of my selling price. And now we play the game. But when the customer chooses to buy or sell, the customer is constrained to use the prices that come from the one side. There is no two sides. And the rest follows, just as you heard yesterday. You can the difference is that when the bookie is giving the pair Q lower bar, Q upper bar, then when the customer says, "I want you to buy," then you're using a value no larger than Q lower bar for the bookie. Bookie won't pay more than Q lower bar to buy. And if you want to sell, the bookie says, you have to pay me at least Q upper bar. And now you can put those constraints in and play the game the same way. It has to be uniform dominance and all that kind of stuff. And you wind up with closed convex sets of problems. Because these are including the boundary. There's a whole literature about how to handle the boundary. It was correct yesterday in warning us that if you want to get the boundaries exactly right, it's hard mathematical work, at least I think it's hard mathematical work. Author and I do some work. I mean, everyone in this area does something with it. But if you try and be as generous as possible to allow the maximum combinations of open and closed, and where the boundaries in and where the boundaries out, and you want to get that exactly right essentially. And it doesn't require infinite state spaces to make the problem. Is there anything you want to say about it? Yeah. So basically, the interpretation of these lower and uppers from Diffinetti's point of view departs from Diffinetti, because Diffinetti would say, if you're going to make a choice and it involves this quantity or uncertainty, think about the quantity, get a fair price, and then make your decision. Until then, all you have are these uppers and lowers, but he would not like you to use the uppers and lowers the way Ellsberg suggests they do. And the way we're following the literature, you're allowed to follow Ellsberg style thinking, and that's not Diffinetti style thinking. Okay, that's all I want to say about that. And I want now to start. How much time do I have left? Please, Kevin.
49. Next break is lunch at 12:45.
And now I have a little under an hour, 55 minutes, something. Okay. Okay. So now I want to look at what is the material in slide 2, and we want to talk about value of information as conditional probabilities. So 2 parts. First is to look at the called off, that's to understand Diffinetti's treatment of conditional probability. Herder was endorsing that as a way of understanding conditional probability. He actually introduced some conditions which are different than Diffinetti's, so I want to talk about that. But the basic theme is one that I want to emphasize common to the 2 approaches. So we're back to the 2-sided pricing. We can do the 1-sided pricing afterwards, but I want to just get clear what already you're inheriting from the 2-sided pricing. Because 2-sided pricing is an allowed picture. You're allowed to be precise. It's not required to be imprecise. So let's see what the 2-sided pricing. So the question is, what kind of contingent pricing, given an event occurring, that you make sense of? We were doing contingent pricing already, or contingent thinking, in that first example that I bumbled so badly in the morning, where I was talking about state dependence, where the second player is making up a strategy. That strategy is formulated with contingencies. If player 1 plays top, I'll do this. If player 1 plays bottom, I'll do that. Those are contingent strategies. They're formulated ex ante. The strategy is formulated before seeing how the player 1 plays, and you commit to the strategy. That's the idea behind these called off gambles. The bookie now is asked to give contingent prices for X, given that an event F occurs. And what does it mean to do that? Well, the gambler again chooses strategies that produce a payment for a contract, which if you look quickly, look just like what we had before. The difference is there's an indicator variable for F in there. So if I hide that, it looks just like what we had before, only now there's an indicator. And so when the event F fails, if the state omega occurs, which is in F complement, F of omega is 0. And when you multiply these terms by 0, it's 0. So it's equivalent to abstaining. There's no change of resource either way. It's a zero-sum game, but there's no exchange of funds. So this is a contract which, if F fails, is equivalent to abstaining and only involves what looks like the ordinary exchange in case F obtains. So the bookie is asked to formulate contracts that are contingent on F, because if F fails, there's an abstention. But you formulate that before you learn whether F obtains. It has nothing to do with learning about F. It's exactly like, what would you do if? So when F fails, the contract is void. You're saying, well, if F obtains, then we'll get into an exchange. I want to understand how my pricing for X depends on F occurring. But what do I think the fair price would F be? Suppose that F occurred. But I'm doing that now, yes.
So here's like conditioning something before it happened, right? So it's
This is exactly, I'm using the word contingent pricing because it's a price that you formulate now, even before you know what you're imagining, you're supposing. Just like the strategy in that morning game, player two, it's formulating a strategy before player one plays. What would I do with this? What would I do with that? The if is a contingent.
It's slightly different from these.
Well, we'll come to that. We'll come to that. In one ways, it's the same as Bayes. In other ways, it's very different from the way Bayes' rule is interpreted. That's where I'm headed. So Diffinetti established that if you're adding these kinds of contracts, so you're asking the bookie to give you unconditional prices and also contingent prices. You have to present that. The unconditional prices were the ones that we looked at the morning. So I've got a price on XI, and then I've got a price on XI given contingent on F. And Diffinetti's theorem says that the game resolves in such a way that the bookie is exposed to a sure loss, or the bookie is immune to a sure loss, if and only if the following happens. We all know that the unconditional prices have to agree with expectations for some probability. There's at least one probability that the unconditional prices agree with their expectations. The contingent prices have to agree with the conditional expected utility in the mathematical sense of conditional expectation associated with those random variables given F. If F as an event has a provision itself that's greater than 0. If F is treated as a null event, this gets us back to the problem we were discussing before about what happens when you have a contingent price given an event that has probability 0. In Diffinetti's theory, you get no constraint at all. There's no constraint on the conditional price, because what Diffinetti's theorem is basically is establishing this holds of pricing events, where these are the contingent prices. If B has probability 0, then this term has any value you want, assuming 0 times that is 0. So this puts constraints on the contingent pricing only when the conditioning event or the contingent event itself is not null, and Diffinetti allows null events to occur, which is different than the kind of theory we were looking at yesterday, because the boundaries had to be assigned positive provision. If you want, well, there are two ways to go. You can say that the probability must be assigned positive provision if you're using pulled off, or as if I read the slide that Gert was doing correctly, he interpreted the coherence as looking only at states that were within F. Like, I don't know. That is, coherence was formulated only for the set of states that were within F, not on the whole space.
I said that in that case, you can drop the extra condition of positive.
Yeah, but that's changing Diffinetti's standard. Because Diffinetti says, since it's contingent, you have to look at losses or gains. If anything occurs, if the event fails to occur, the fact that you lose when it does occur doesn't cause you to be in book. If you're not losing anything, suppose, for example, I'm only asked to give one condition, one contingent price. What's your price on the event A given the event B? If I think B is null, that's probably my provision for B is 0, then I can say something crazy. Like I'll give you a provision for A of 2, the indicator function of A. You should have a price of 4, no greater than 1. I can say 2 given B, and I won't be in book, I won't be a short loser by Diffinetti standard, because if B fails, it's the probability B given A fails, then I haven't lost anything. It's a null. You don't have a uniform sure loss. It's just weak dominance. They're not violating. So Barrett at one point formulated the value of the condition that corresponds to weak dominance, which is not Diffinetti. So when you get into these subtleties about the probability of 0, you have to keep your eye on the mathematical details. Diffinetti does it this way, and when he does it this way, it's called off. It's unconstrained in the conditioning event. It's null, and so you don't get it for there. But if the conditioning event is not null, the only pricing that satisfies his requirement of coherence is that you use the conditional expectation, because this is the theorem that he's verifying. Not, you can't go dividing by P of B. B has probability 0. Okay. Now, I want to use this to remind you something that is not part of Diffinetti's theory.
Contingent pricing, the pricing you place when you're playing this game with cold off gambles, involves no change of information. You've learned nothing when you're asked to price X given B. It's a contingent, it's all static. The bookie is offering a price for X on the condition that F occurs, not on the condition that the bookie learns that F occurs. So let me say that again. It sounds like I'm making a mountain out of a molehill, but this is not true. The contingent pricing is what's your price on X given that F occurs. It's not contingent on what's your price on X given that you learn that F occurs. Those may be very different events. X occurring and learning that F occurring and learning that F occurring are very different events, quite obviously. The pricing that you make is the contingent pricing. What's your price on X given that F occurs, not given that you learn that. And in game theoretic situation, this is very different. Different between the opponent doing F and learning that the opponent does F. The reason I pound the table on this is because the Bayes rule of learning reads typically as the following. At time t0, you have a coherent two-sided prices and contingent prices agreeing with the probability P. At the later time, you learn that the event F occurs. How should you change dynamically your pricing between T0 and T1 when you learn F? The usual formulation is you should work with the initial probability and use the conditional expectations. That is not required by Diffinetti because Diffinetti is static. The later time, I could treat myself as a completely different agent and start with a completely different set of prices. There's nothing across time. And the second, and this is the point I'm emphasizing, and this is not even a correct use of conditional probability because the conditional probability should be the total evidence, which the total evidence of the later time is not really that F occurred, but that I learned F occurred. Well, I'll show you the effects of this on game theory. Does everyone see though what I'm pounding the table about? There's a difference between, if I'm using it as a dynamic rule, I'm supposing that at the later time, not only did F occur, but I learned it somehow. And the question is, how should I update my opinions when I learn that F occurred at a later time? And the usual rule says, forget about the learning, just go look at the contingent pricing on F. Well, contingent pricing had nothing to do with the fact that you learned it, it was just that F occurred. There might be important situations where my reaction to X is different when F occurred than when I learned that F occurred. If you want to see the effects in statistics, go look at the difference between experimental data and observational data. In observational data, the whole point is I distinguish between the fact that I learned something as opposed to just that it occurred. In observational data, I'm not under control fully of what I observed. The fact that I observe it is part of a certain process. Will I observe it alone? Depends on whether the person responds to the survey. If I'm not able to control that, then there's a difference between the person non-responding and having the value there and the person responding.
So can you say again why you are assuming that after you learned F, you also learned that you learned that?
Because my total evidence is that I learned it. There's no collateral uncertainty.
You just assume.
Well, am I aware that I've learned F? In the sense that I'm using an update rule. This is Bayes rule is supposed to be given as an update rule. It says between now and earlier time and now you have learned F.
So you're saying in order to apply.
Yes, that's right, that's right, that's right. In order to apply it, I am assuming that the total evidence is that I've learned F. But that's not the event I modeled as the contingent event when I set up my conditional pricing. When I set up my conditional pricing, it's just an F occurs, not that I learned it or when I learned it or how I learned it. And when I learned F, all that extra information comes flooding in as well. I've learned F, you can say, well, hey, how did you learn it? When did you learn it? All of that might be pertinent to the conditional provisions I said, not part of the usual Bayes rule. So I'm pounding the table on that because when we watch that, we get some interesting results, particularly about
So just to clarify, I'm not entirely sure I get it. So is it that because the original formulation of how the pricing is static, and so that works with not learning the F occurs, but just looking at F occurs. And then Bayes rule is trying to do that, use that to get a dynamic setting, and then you're basically saying, well, that doesn't work because the dynamic setting, you would have to consider conditional that effort is not learning that effort.
That's right, that is a total evidence at the later time. It's not merely that that occurred, but it's that you've accepted it as evidence, and you've accepted it as a condition. Because you want to say, I've learned it. I mean, you're treating it as true or certain or something like that. And now you're supposed to use the update rule, but the update rule is taken as the conditioning event just as the event occurs. And I'm emphasizing that quite obviously we want to distinguish events occurring from learning that events occur. And if the total evidence is that I learned that occur, then if we're going to apply Bayes' rule, it has to be that the initial event F that we're taking as contingent is not just that F occurred, but that F occurs and I learned it in a certain way in time to be able to apply Bayes' rule later, which is a very different event. Notice we've taken innocuous events and loaded them with all kinds of epistemic bells and whistles, like learning things. All of a sudden, our state space has to include not just ordinary mundane events, but epistemic events. And my probability now has to get very complicated. It's very complicated.
We say that in for Bayesians, we assume that the agent is an undecided. This is at each point of time, he knows what occurred so far.
We're assuming at this point that we're doing defining that at each stage the agent has this state space of certainty. That's what reflects what we know. The omega, the big omega. The state space of certainty because all the random variables are defined on it. And that's supposed to be the omega is supposed to be the sure.
I'm trying to say that the reason that we don't distinguish between Bayesians and don't distinguish between F carrying and agent learning that F carrying is that at the stage we assume that everything is a carry, the agent knows, the agent is there.
Yes, and I'm saying one of the things is that if you're going to do that and apply Bayes' rule, this is repeating what we just said a few moments ago,
Yes.
is that then you need the F that you're conditioning on already to include that epistemic information. And that means the initial state space has to be this complicated state space, which involves not just the ordinary events, but events that are modified by when you learn them and how you learn them. It's all that will be. And so you can use Bayes' rule for updating. If you're going to do that, which is not part of the definitives theory, be aware you're committing yourself to having a state space at the initial stage, which includes not just events occurring, but when you learn them and how you learn them. And I don't see that going on in the Bayesian literature very often. I mean, the statistician community, system community is aware of it. Bayesians who deal with observational studies are compelled to face that because they have to model the observational aspect of observational data. You might observe it, you might not observe it, so you have to model when you observe it, which is picking up when am I going to learn it. But ordinary philosophic literature, if you go read Carnegie, for example, I think there's not a hint of this problem anywhere. Yes.
Just a side question, classical probability the condition by restricting the SIPTA to some sort of overlap. Yes. So just my question is this way of conditioning classical probability, do you think this corresponds to this scaling constraints?
Yes.
Or do you think it's a technical notion that can be interpreted for grades?
So, Julia has correctly pointed out that there are some, not all, theories of conditional expectation which handle the conditioning event by restricting the state space to just the elements in that conditioning. This is related. There are several technical aspects of that that relate to what we're doing. One has to do with the probability of zeros event that we just discussed. It winds up not being any treating the probability of zeros more restricted. But with regard to the topic we're discussing now, there's still the difference between restricting to that and learning that that restriction obtains. Let me say that again. Why are you restricting it? Because I learned something. Does the learning of that also reflect your uncertainty in whatever you're going to decide? And there's a difference between just restricting it, which you can do statically, and saying the restriction also applies when I learn. Saying what I'm saying is when I'm being persistent and sticky about is that when I learn it, I want to treat that as a different event than just that I restricted it, because that's correct, because one of those things happened. Something else is happening for me. And there may be relevant information from that. I need to know.
If I understand correctly, I just want to make sure.
Yeah, I think it's important, so I don't mind saying
So
that.
when I think of basically taking accounting about conditional expectations,
Right.
and when you say that some event F occurs or something, what I think it does to my space, so I have some space, right? And so it kind of creates a Boolean subalgebra in that space.
Sure, a linear subspace if we're going to distinguish it down.
So if I update on that or learning on that, it doesn't change it that I use conditional expectations, I create different.
Very different ones, that's right.
Okay, so
And what I'm saying is that the usual formulation allows you to start with an ordinary mundane space that has ordinary events in it, nothing about who learns what, when, or anything like that. And that space will be too weak to properly model the total evidence when we try it. And the usual formulation of Bayes' rule for updating it never mentions it at all. You pay the price for that when you start to do observational studies, where we try and model situations where the part of learning is relevant. Games, this is what signaling is about in games. It's not just that this occurred, I was signaled that. That may be telling me something. We'll see how to use that. Thank you. That's why I'm pounding the table about this, because I think it makes a difference for what you can do with IP in a favorable way. But it's a fault in the original formulation, if you're thinking of Bayes' rule for updating. Okay. Let's now use Bayes' rule for updating with all that work. So here's how much time, Kevin?
35 minutes.
I'm going to have to cut out something, but that's all right. I'll tell you what I'll cut out in a minute. So there's a result I'd like to discuss, which is the value of information, which has a certain very intuitively satisfying, certainly to academics, you'll see why, intuitively satisfying result when you do precise probability, which when you do imprecise probability opens the door to some anomalous results because we have new cases that are not covered by the original theorem. And the theorem has to do with the value of information when we're using Bayes' rule for updating. So this is the kind of problem I want to look at. The mathematics for this is simple. We won't need to do proofs, but since it's such an elementary proof, I wanted to put it up. I'll put it up in a minute, but let me get the problem for you this way. So it's dynamic. You are here in the map sense. This is a temporal map in which the box is a decision point and you have k terminal decisions, right? So there's some state space, omega n, and finite, that's fine. And you've got k options, d1 through dk, rows. Suppose you're an expected utility maximizer, and d star maximizes expected utility, no moral hazard, keep everything simple. When you're facing just the static choice. Suppose, however, we're going to actually introduce the opportunity for sequential decision, where now you don't have to choose one of these k options. You're allowed to choose to observe x. X is a random variable. And x has m possible options. And you will learn the value of x. So you'll learn x equals x1, or x equals x2, or x equals xm. And then you will make the choice, not with respect to your initial information, but with the updated information, learning x. This part is held the same in the sense that the decision matrix with regard to the omegas is identical, same states, and the outcomes are not changed. So these are all the same k options in every case. You're basically just postponing the decision to learn something about the states. Everyone following? And then you make the choice. So the question is, what strategy, if we were doing the extensive form, which is the sequential form, you would do the backward induction. You would say, okay, if x equals x1, then what would I choose? Well, you're going to use Bayes' rule for updating and use the conditional expectation given x equals x1. That will change your probability on the states, perhaps, even in a way that leaves d star still the best. So this says that if I've learned x equals x1, even though my probabilities may have changed, d star is still the best. However, if I learn x equals x2, then my opinions change significantly,
at least D1 now becomes best. So I'm highlighting, so this is the backward induction. So I'm saying X equals X1 value X star, X equals X2 value D1. And these are the conditional expected values associated with these best options. And so from my initial point of view, the value I would associate with X would be the expected value of these conditional expectations. These are all conditional expectations. This is the conditional expectation of D star given X equals X1, which is the best of those K conditional expectations and so on. So I've got values here, and I'm taking the expectation of those values. Does everyone follow that? So that assigns a single value to this sequential option. I now have K plus 1 options. I have D1 through DK initially, or initially the value I am assigning initially to learning X. The theorem says that assuming there's no value in this process of learning X and making these calculations, the value I associate with that branch is at least as great as the value I assign to any of the other K options. That is, the value assigned to D star at the initial point is not greater than the value I assigned to the sequential option, my strategy of learning X and choosing D star of X1, D1 of X2, and so on. And the theorem says, if on an event here, let's suppose these are all positive probability events initially. I say X equals X1 with positive probability, or X equals X2 with positive probability, or X equals XM with positive. If they're all positive, and as in this picture, there's at least one branch where it causes me to change what I would do. It says if I learn X equals X2, my strategy is to choose D1, not D star. Then the value associated with X is strictly greater than the value I assign to D star initially. So that is a very neat result. It says, given this opportunity for cost-free information to postpone a decision, never hurts to go that way. And if the information were to change my behavior, even in one case, as long as that case has positive probability, the value of the information is positive, I would assign a greater value to postponing to learn. This is the model of tuition. I can charge you for X as long as you agree it might change your behavior. You want to pay. If everything I tell you is like pure philosophy and it wouldn't change what you do, then you don't want to pay for pure philosophy. But if I'm telling you something that might change your behavior, then I should be able to charge you a little tuition for it. That's why I don't teach pure philosophy. At least I don't think I do. Everyone understand the picture of the theorem? It's formulated. Whoops, wrong machine. The theorem gets formulated. Again, this is our original decision space, D1 through DK. This is what is persistent through all of those. You always get to choose from D1 through DK with these as the states. I'm using S as the states and the same outcomes. That's never changing. What you're learning is information about the S's. And this is just summarizing what I've said before. This is all summary, and this is actually the 3-line proof of it. And it uses a theorem that we need to keep our eye on. It's this theorem, ain't no theorem for IP. It's only a theorem for precise probability. The theorem that drives this trivial result, mathematically trivial, conceptually important, is the following law of conditional expectations. The price you put on Y has got to be the price you put on the conditional price of X of Y relative to some random variable X. So if you go through and look at your conditional prices of given Y given X, the price for that conditional price has to equal your unconditional price. The expectation of your conditional expectations is your unconditional expectation. This holds for finite partitions or countably additive probabilities. It's basically the law of total probabilities, just write it out. We could do the proof in 10, 15 minutes, but I don't want to bother you with it. Certainly for bounded random variables and finite structures, it's trivial. But then you see how the proof goes. The way you do it is to say the expected utility assigned to an act D, which maximizes the initial problem, call that D star. So the expected utility here. The expected utility assigned
D star up there has to be the expectation of its conditional expected utility, given I calculate the value of D star given x equals x1, the value of D star given x equals x2, given the value of D star given x equals xm, and take the average of those, the expected value of those, that's the same as the value I assigned to D star originally. So the strategy which says ignore x and always choose D star initially has the same expected value as the value of choosing D star. Now, as well it should, because what I'm saying is I'm committing myself to a strategy which says, regardless of what I see, I'm choosing D star. What value do I assign to that now? Well, that's the value I assign to D star, and the mathematics confirms that. So the value of choosing D star in every case is the value I now assign to choosing D star, and that was the best of those. And here I'm doing even better, because here in x2 I'm choosing D1, which has a higher expected utility than D star. And when I average those numbers in, I get a higher expected value than D star. That's the proof. And now we're going to look and see how this fails, because life is not always like this. So, but why is I'm saying this a marvelous result? This is the academician's first principle. Never decide today what you can postpone till tomorrow. I mean, you're not academicians. Why you said, of course, I might learn something which will improve my health. You're correct. And the value, the theorem says it might not be relevant, but the value is, it doesn't hurt to postpone if you can postpone for free. But the only time the value of the information will be zero is if and only if the new evidence never gets you to change. Even if it could change in only one circumstance, good enough, it's worth running the experiment. And this is the beginning of the theory of experimental design from subjective expected utility. The difference between choosing now and choosing the sequential option can be thought of as the value of conducting the experiment X. And now you can run this analysis with different kinds of designs. Fixed sample size 1, fixed sample size 2, values of X. I use X repeatedly. Which is the design? If there's a cost associated with observing, this tells me how to evaluate the value of learning information with regard to some basic decision. What's our pilot study should I take? So the material in the appendix to this set of notes goes through exactly that, following an analysis out of Maury de Groot's wonderful book, Optimal Statistical Decisions. So it's basically using this theorem, assigning a value for experiments reflecting the fact that the experiments may not be cost-free and folding in the cost. And then saying, when should I stop? What strategies are the optimal strategies for stopping this theorem? Yes, Chris.
So I see from your argument that if you were going to use this case, it still work as long as you have the power in.
That's exactly right. This is important for your work on. And now we're going to look at the case where the power property fails, and imprecise probability says I can learn something which I would assign negative value, plus negative value to, in the sense that I prefer not to learn. I want to close my eyes. So one of the lessons anyone learns who works on extending theories, if you make a theory more generous, it will let more things in the door. You have more responsibility for applying theory reasonably, because it can be applied in a crazy way, in new ways. That is expected utility, even if you're an expected utility maximizer in different theory, that doesn't prevent you from having crazy priors, crazy probabilities. I mean, it can be coherent in the technical sense to think that the Earth will be destroyed this afternoon. Not incoherent. It's crazy, but not incoherent. When you go to IP, there are more ways to be crazy. And one of the ways to be crazy is to seek information, is to expose yourself to the possibility of information of negative value. So let me show you how that works. So how much time, Kevin?
20.
Good. So we're going to skip a part of so I'm going to skip something which is related to moral hazard. Let me just tell you what the result of this section is. We can come back to it if you want to discuss it. It's pursuing the question of what does moral hazard do to this value of information. And the simple answer is the theorem is sensitive to moral hazard. If you have the opportunity to learn information, which just choosing to learn the information changes your probability on the states, then the theorem doesn't hold. And the reason I mention this is because it applies in game theory, where players can purposefully want not to play the game with more information because of moral hazard. So let me say again what I'm going to skip. This section in here begins with a trivial decision problem where we know how to introduce moral hazard. This is the example I bumbled so badly at the beginning, but you saw the point that even though Act 2 dominates Act 1, if there's the right act state dependence, then you don't, Act 1 may be the better one. That will interfere with the power expectation. The power expectation only holds when there's no moral hazard. Let me put it that way, if choosing to learn X changes the states of probability even before you observe X. Why? Because I'm setting up an experiment. I have to learn X, I have to set up an experiment. That experiment is something in the world. Maybe setting up an experiment changes my probability on the states. That's already enough to make the value of information. And then this can occur when the states are in a game. And what I've got here is, since I teach game theory, there's a book I use, Osborne's textbook, Marvel's textbook, Introduced to Game Theory. He has a little section I quibble with, not for the game, but for his analysis. He says, let me show you something that can happen in games which cannot happen in decision theory. I'm paraphrasing really closely. And what he gives is this game, which both players, the situation is that there's a state omega 1 and a state omega 2, which affects the payments to a column player, not to a row player. The difference is for column player, the consequences of M and R are commuted between state 1 and state 2, just the way I bundled the construction this morning. State 1, M in state 1 is R in state 2, R in state 1 is M in state 2. Other than that, it's only affecting column player, not row player. And the first version of the game, both players don't know which state they're in, but assigning probability of half and know that, and you get one solution. And then if you allow player 2 to learn the state before choosing, cost-free, and player 1 knows that, then they will wind up in a different solution solved by dominance, which is Pareto inferior. Both disprefer the outcome. Let me say that again. There's a solution to this game when both players don't know what state they're in. They're choosing left, middle, right for column, top, bottom for row. And their payment is the average of the two, which only affects column player, because row players payments are the same. And in that case, they would wind up with bottom left. That turns out to be the solution by dominance. I won't take you through it. But if you allow column player to learn the state before choosing, and row player knows that column player will choose it, that dominance contingent on learning the state has column player choosing right if state 1 and middle is state 2, because 3 epsilon dominates 0 and 2 epsilon and 3 dominates 0 and 2 and so on and so forth. And if column's doing that, then row chooses top, and so they wind up with something that's Pareto inferior. So this is used as an example how game theory players may strictly prefer not to learn cost-free information. And I'm saying, yes, that's correct, but Osborne is not correct to think this is only in games. This will happen when you have absolute dependence. That's the answer. So the point is, the reason this is happening is because some act state dependence. I'm going to skip that. You're welcome to look at my analysis. And I want to jump. So how much time? Yeah, good. We should be able to do this in 15 or less. So I want to suggest that there's another way that value of information is all not only can fail, but can be turned on its head with negative value. And that's it said even right away what's going to happen. He's going to say we're going to see cases of IP with the law of conditional expectation to the power property does not hold. Doesn't hold. Now the example I want to use
So the information is cost-free, but the analysis will be, I strictly prefer not to learn, even though the information is cost-free. And the example I want to use for this, which is dependent on IP, you can't do this in precision, is based on some old work. It's now 30 years old that Larry Wasserman and I worked on. But I mean, many people have worked on it. We just have to, I think, get there early enough to be able to name the phenomenon. That's maybe one of our, we call it violation. Let me tell you what the phenomenon is. Let's suppose right now I have a non-trivial IP model for the event E. I have a lower and an upper probability, lower price, upper price, however you want to think of it, which is not the same. So P lower star E is my lower price, P upper star E is low. Let's not worry about endpoints, suppose it's closed interval. And let a random variable X be defined, finite, such that the following happens. I'm defining something, I've proved it exists, but I want to define it first. Let's suppose that when I learn Xi and use Bayes' rule for updating, so I take each of the probabilities in my set and update each probability by Bayes' rule, it gives me a new set of conditional expectations. So I'm using Bayes' rule to update the set by pointwise updating each probability in the set with the same information. When I look at this, the lower probability for E drops down and the upper probability for E goes up. So the interval P lower bar, P upper bar for X equals Xi is now a bigger interval strictly. And suppose this happens for every Xi. So no matter how the experiment turns out, my interval dilates. The bottom goes down, the top goes up. Okay? Now, the decision theories associated with this phenomenon can generate negative value of information because a certain act that was not optimal initially may be robust in the sense of Ellsberg. And when I learn the conditional expectation, its value stays nice and tight, but the other things start to dilate in value. This act doesn't depend on X. Its value is, it's a robust expectation, doesn't depend on X. But other acts depend on E. That is, the value depends on the value as probability assigned to E. And so the dilation can change the value. Something that was best before can suddenly behave like an Ellsberg phenomenon that has a range of values. And if the bottom drops down, then I may choose the robust one. And if I'm choosing the robust one, then if I've learned information and I choose the robust one, I may not want to learn that information because before I learned the information, without learning the information, it was something that was higher. So something that had a higher expectation can become Ellsberg-like and become non-robust in value. I'm waving my hands. Let me show you an example. That may be the simplest way to show you. So now I'm going to give you an illustration because all I did is define directions and it's not possible. So here's a simple example. Suppose A is a sufficiently uncertain event. Its lower probability A is near 1, its higher probability is near 0. So lower probability is near 0, higher probability is near 1, just as a toy example. So A, I'm highly uncertain of an object sense. Let HT be the outcome of a flip of a fair point that I take to be independent. So this is kind of the point I would use for randomizing mixing strategies. So the probability I assign to the combination A and heads is half the probability I assign to A for each probability in the set pointwise strongly. P of A and H is P of A over 2 for each probability in my set. Okay. Now look at the table, which is a 2x2 table. I've got 4 atoms in my space. A in heads, A in tails, A complement in heads, A comp, and that creates that 2x2 table. And let me just allow me to define the diagonal event E and E complement. So E is A in heads or A complement in tails, and E complement is A complement in heads or A and E complement. A complement and E and tails. Again, let me say it without bumbling over. I've got the two events, A and A complement, and a flip of a fair point, which I take to be independent of A. And I define the diagonal events. The diagonal event is E and E complement. E occurs if either A in heads occurs or A complement in tails occurs. And the event E complement is the other two atoms, A complement in heads or A and tails. Okay? These would be recognizable in statistics as what are called pivotal events. Why? Because the probability of E and E complement no longer depends on the uncertainty about A. The probability of E is, the probability of E initially is a half. Why? It's A and heads, union, A complement and tails. The probability of A and A complement sums to 1. So it's a half times the probability of A plus a half times the probability of A complement. It's a half, regardless of the probability I assign. I can be uncertain about A, but with regard to E, E is robust with regard to that uncertainty. It's a constant probability of half. It's like in most groups. I know the probability of E is a half, even though I don't know the probability of A precisely, to use that line. Everyone follow it? So let me go through it again. Because H is a half and independent of A, in any for every probability in my set, the probability of E is the probability of A times the probability of H plus the probability of A complement times the probability of T. That's a half times probability of A plus the half times the probability of A complement for every probability in my set. Probability of A complement sums to 1. So that's a half. So the lower probability of E is the upper probability is a half. This is robust, doesn't depend on the probability of A. But if I were to learn H, now you see this becomes Ellsberg line. Because given that I've learned H, the probability of A is the conditional probability of A given H, which I'm saying H is independent. The probability of A is this uncertain thing. It's nearly 0, 1. So the lower probability of E given H is near 0, because it's the probability of A given H, which is the probability of A. And the upper goes towards 1. And so you have dilation for heads and you have dilation. This is the IP problem. This is the IP curse of conditioning. Because you can take an event that is robust, E, and make it Ellsberg-like, dependent on some parameter like conditioning. So I've taken a mixture in such a way, I've randomized. By the way, this also is a way of appreciating one of the experimental importances of randomization. Because what I'm doing with heads and tails is randomly choosing between A and A complement. And I'm doing so in such a way that my uncertainty about A and A complement is washed away. And that's what you're doing in part of randomization design. It's exactly this kind of phenomenon. A randomized design is creating exactly these kinds of probabilities for E complement or pivotal variables if you're doing statistical inference. Okay, so now the problem is you can see where this is going. We can make up a little decision problem where the value of information is going to be negative if I choose as my decision rule something like lower expectation. Because the lower expectation of the favorable act will drop below the lower expectation of the unfavorable act. Yes. Okay.
Yeah, just a simple question. So in this on time before, so when you now conditionalize on H, is this now you're still thinking about H occurring, or is this now I'm not just thinking about?
I'm saying let me wash away the problem I started with about learning, and saying we'll assume that the experiment is such that I will observe, I will flip a coin, and it will speak heads if I observe its heads. So that's one of the ways of attending to the problem I talked about, the difference between effective learning, is to say I'm designing my experiment so an observational problems don't occur. And one way is designing a rigorous experiment where the sample space is such that I know what the sample space is and the outcome coincides with my learning. Under those conditions, my concerns about learning go away. And that's one of the points about good experimental design. It's the reason why you want an experiment rather than an observational study,
Because when you do an experiment, the Bayes rule of updating will be exactly the right thing to do, because there won't be a difference between the right and the learning it. You design the experiments and you see them. So you can pretend that we're learning. So let's suppose the point is always a thousand. Is that answer? Yeah. The reason I mentioned is not for this situation, but when it comes to learning in games. Because in games, I don't have an experiment that tells me what the other person is learning. I don't have an experiment to learn what your down cards are. Okay, so here's a terminal option. I ask you, what would you, so this is a choice between a terminal option and a sequential option. The terminal option is win 75 if you lose 125 if you complement, that's 50-50. So it has a negative expected value. The sequential option X is observe the coin flip, heads, tails, and then choose between an even money bet on E. And notice that D2 is, D1 is D2 with a 25-cent fee in. Sorry, I left these in dollars. And D3 is a fee of 50 cents. Now, in the sequential option, if I just look at the backward induction, I'm saying, okay, how will I choose between D2 and D3? Let's just assume I've taken the sequential option. How will I choose between D2 and D3? D2 is an even money bet on E, but notice, given that I've learned heads or I've learned tails, the value associated with E has a lower end of almost surely losing the bet and an upper end of almost surely winning it. So the lower expected value is going to be loss of $1. Remember, it's Ellsberg type. So if I'm using something that looks at lower expected value, the lower expected value of D2 is very bad. It's -1 nearly. And so between D2 and D3, I would choose D3. I'd buy my way out, buy insurance at 50 cents. D2 is a highly risky gamble in terms of expected value. It's got a range of expected values from -1 to +1. Conditioned on I've learned X. And so I might, Ellsberg style, choose to buy insurance, which takes me out of that. Pay 50 cents, unload the gamble. However, so the value of the sequential option is lose 50 cents, which is worse than the expected loss associated with D1. D1 has a value of -1/8. So right now, D1 has a value of -1/8, half of -1/4, half of +5/4. Yeah, so 1/8. Yes.
What was the decision rule where would you?
Lower expected utility, maximize minimum expected. I'm looking at the lower end. We can look at more complicated. Gamma maximum, which is to maximize minimum. Ellsberg style, that would be the kind of explanation for the Ellsberg pattern. I'm looking at the lower end, how bad is it? It's a kind of extreme case, but there are lots of rules that will in the end resolve by looking at lower expectations. And I'm just jumping right to that. We can have more convoluted versions of do this first, do that first, and then others, things that are unresolved, eventually we look at lower expectations of security. And to the extent that security matters, the security is dropped way down. Yes.
So in 3D4, the terminal options were the same in the starting point and after the burn.
Yes.
Are there examples where this happens also in such a?
Yes, I'm just doing a simple example rather than a more complicated one. It's close enough. We can tweak this back to the version of the theorem. But I'm simply saying the point here is that in this case, you'll see that you would pay not to learn this information. Pay not to learn. That is, the value of the terminal option, D1 is -1/8, and the value of the sequential option is -1/2. And so it's worth you not, you would pay a little bit to stick with the terminal option rather than actually engage in the sequential option. It's the reverse of the, yes.
This is kind of a philosophical side.
Yes, please.
Yeah, so you introduced this by saying, you have to use the theory responsibly.
Yes.
And not do crazy things. So
Right.
compared to radical, these radical steps.
Right.
Now it does seem like there's something to be said about why it's crazy to have, these weird
Right.
priors.
Right.
You can kind of roll out on formal grounds.
Yes.
But this just seems like totally, like you totally. agree.
What's crazy about
So,
this?
what's crazy about it?
So I'm saying is, you don't want to design experiment. There's a responsibility in designing an experiment. So here's again, I'm going to take my pragmatist position and say, learning is an active responsibility. My model of learning is not passive observer. I don't sit here and just get them bombarded with observations. That's not my model of learning. I'm not a passive learner. I'm more of a doing.
But the world might throw this at.
Yes, it could happen and I have bad luck, but I'm saying at least I want to take responsibility. I can't protect against bad luck. There's lots of bad things, way things can be bad. But I do at least feel that if you're going to do IP theory, you have to be much more careful about the theory of experimental design than you are with traditional theory. Because traditional theory has a fallback, at least if it doesn't cost you to learn anything, you can postpone, can't hurt. I'm saying yes, it can. And so be careful about what you're planning to learn. That's the responsible part. So you're crazy in thinking that, oh, I can learn any old thing and we'll design any old experiment. And of course, it can't hurt. No, it can't. It can polarize it. To use a different. So what this is going to do is anticipating if the initial range of probabilities had to do with different subjects, different people, excuse me. So that range of probabilities was a community. The community has got consensus about the event. They all think it's 50-50. However, you would polarize their opinions if you gave them the information about their stance. There's reason, I think, if we look around American society, at least currently, about not wanting to design experiments that polarize opinions. IP theory opens the door to polarizing opinions. That's what I mean. So that you're asking what was the craziest that I'm saying it would be crazy to take a society and subject it to mandatory polarization. And that's what you can do with IP theory. You can't do that with traditional expected utility theory. But traditional expected utility theory doesn't model groups well. So if you're thinking of the IP part as being a candidate for group decision to do the ethics, then you have a responsibility about what you're serving as the public information. And you can polarize the public information in a way you can with single. Does that cash in a little bit of the IOU than I did when I say you can be crazy with expected utility? You can also be crazy with IP.
Yeah. I'm not sure it's quite analogous.
Well, it's not. It's a different kind of craziness. Right. I'm saying I would think it's not constructive to formulate experiments that are designed to polarize community opinions. And if you want evidence of that, just look what's happening in states. I don't think that's a wholesome way to run a society. IP theory allows you to do that. I'm saying, well, the responsibility is don't conduct those kinds of experiments, find other more useful things. I don't know, maybe my politics is showing through too much.
We get Ellsberg.
Excuse me?
We get Ellsberg on this.
Yeah, we can force Ellsberg on it.
Or no, we get Ellsberg the guy.
Oh, yeah, yes, that's right. That's right.
You don't want to force that.
Okay, I think, so now the rest of the paper is, the rest of this is telling you results about when dilation occurs and when it doesn't, the bounds and all that. I summarized it. There's a model which is very close to the model. How much time? 5 minutes? Or so there's a model here, which is a generalization of the model Bert ended up with yesterday. He did it for two elements. It's called epsilon contaminated model. And this is the generalization to more than two partitions of that result of the epsilon, and gives you all the violation conditions for that. So this would be, if you're using that kind of epsilon contaminated, what you would do, what you want to avoid in order not to polarize the community. Okay, I'll stop there.